Hello and welcome to this tutorial on how to run an SEM power analysis. My name is Geiser, I'm an instructor with QuantFish. When we plan a study with structural equation modeling, we often wonder what sample size would be adequate for that structural equation model so that we will have enough statistical power to show the effects of interest, specifically regression coefficients in our structural model or the latent variable model. One way to find that out and also to learn about other aspects of the model and whether they work well with a given sample size is to use Monte Carlo simulation studies. And now this is something that scares many people, especially practitioners who don't care so much about statistics and computing, and they think, oh my god, this is complicated to run a simulation study on something and not something that they really want to do necessarily. But I want to show you in this tutorial that it's actually quite straightforward, especially in the program Mplus, which makes simulation studies extremely user-friendly and extremely fast to run. So preparing this tutorial here literally took me maybe 15 minutes. And so writing the code is really easy for such a simulation, and then also Mplus makes it pretty easy to interpret the results and for you to figure out quickly, is this a sufficient sample size for my SEM? So let's get started and let's take a look at this. So here my first example input and output file that I want to show you is for a simple two-factor structural equation model where I have three indicators or observed variables for each factor, and the factor f1 predicts factor f2 in a linear latent regression analysis. So there's a single structural coefficient, a single latent regression coefficient for the regression of factor f2 on factor f1. And so I want to walk you through this input file here first so that you can see how a simulation is set up in the Mplus software, and then we will see where we can find power estimates and also other relevant aspects of the simulation that would be important for you to find out before you go and collect your sample. So first thing that has to happen in a Monte Carlo input in Mplus is we have to come up with names for our variables. So the names list has the variable names that we make up. So we decide what the variables are called, and that's part of the Monte Carlo command that kind of sets up the key general parameters for a simulation in Mplus, such as variable names, the number of observations that we want to simulate. So we want to know, for example, is a sample size of size 50 sufficient for this model? And so this is what I'm choosing here right now. So a really small sample size, which may not be sufficient for estimating such an SEM. Now, why is it so complicated to figure out the sample size for SEM? It's because it depends on so many factors, including the size of the model, the number of indicators, the reliability of the indicators, the size of the path coefficients. And so therefore a simulation is best to answer the question of sample size for a specific model. Now, another thing that we need to specify in the Monte Carlo command is the number of replications that we want to use in our Monte Carlo simulation. And you can think of these in the same way as bootstrap samples. So here, this is like a parametric bootstrap where we set up a population model and then we draw samples from the model. And in this case, we would draw 1,000 samples of size 50 and then estimate our model in each of those samples to see whether that works well with a sample size of 50, whether the parameter estimates in those samples adequately reflect the population parameters that are specified in our population model, and also whether we have sufficient power to show that parameters that are non-zero in our population model can be detected as statistically significant in our samples to a sufficient degree. So let's say we would want maybe 900 out of the 1,000 samples to show significance so that we have a power value of 0.9. So that would be important. So the number of replications should be high because we want sufficient precision. So 1,000 or maybe 10,000 for a model like this should be no problem in terms of computing power. The seed value is a starting number that is a random number that, so to say, sets the stage for the model. So this is where the simulation begins. Now, the seed number is not really critical. You can pick whichever number you want, but maybe it's a good idea to check different seed numbers to see if the results change for different seed numbers. They really shouldn't, but something to probably do, and rerun the simulation with a different number, see if you still get the same general findings. Next is the model population command, which allows us to specify a population model. And so this is kind of, or this parallels what you would do in GPower when you set up the effect size, for example, for a power analysis for a t-test or an analysis of variance, or in some other power analysis program. So here we specify our effect sizes. So to say, in this case, the factor loadings, the structural coefficients, but also all other parameters that are relevant in a structure equation model. So we need to have a value available for each population parameter of the model, and that's the most tricky part. Like it is when you have to come up with an effect size estimate that is realistic. This is also complicated because often we don't know what loadings to expect, what structural coefficients to expect really. So one approach is to look at the literature and see what others have found with similar constructs or similar variables. Another approach is to simply simulate a whole range of different parameter values to see how that impacts power and other results of the simulation. Also, you can make your life a little bit easier by assuming that the variables are all standardized, meaning in z-score metric, so that you're dealing with a standardized solution, which makes it easier to set the parameter values to values that are realistic. So in this case, I have assumed, or I have set up my population model in a way that both the observed variables y and the latent factors f are standardized, meaning they all have a model implied variance of 1, and therefore the loadings are standardized, and also the structural regression coefficient is also standardized. Now I'll show you how this works. So how do you get that to be standardized? So first of all, I set the loadings to typical values that you would expect for decently reliable variables, where the loadings here range between 0.7 and 0.9. So the correlation between a given variable and its factor ranges between 0.7 and 0.9. So that we have R squared values between 0.49 and 0.81. So that's probably relatively realistic for a factor model. And you can see that I set the factor variance of the first factor to 1. So the factor is standardized, and that achieves identification and also makes the factor a standardized factor that is in z-score metric, because that factor's mean by default is 0, and now its variance is 1. So this is a standardized factor. For the second factor, it's slightly more complicated, because the second factor is the dependent variable or endogenous variable. And so we have to set the factor metric in a different way. So here you can see next I have the regression of f2 on f1, and the coefficient is set to 0.3. So that's my standardized factor regression coefficient, because I'm assuming the factors are standardized. They both have model implied variances of 1, as we will see. And then you can see I fixed the factor residual variance for f2 to 0.91. And so this is done so that the factor variance of f2 will actually also be 1. So let me explain this a little bit more. So in Mplus, when you have a variable that is an endogenous variable or dependent variable, meaning one that appears on the left-hand side of an on statement, then Mplus automatically knows that that variable's residual variance is a free parameter in the model and not that variable's variance. So that's an important, subtle but important difference. So meaning for f1, we set the factor variance because that's an exogenous variable, whereas for f2 we set the residual variance because that's an endogenous variable. And now since I set the coefficient to 0.3 for the regression, then that coefficient squared would be 0.3 squared, 0.09. So that plus the residual variance of 0.91 gives me exactly 1. So then that means that also the factor f2 has a model implied variance of 1.0, and so then I can interpret this as a standardized coefficient. And so it's the same way as we do it with the loadings, where also the residual variances are set to 1 minus r squared, so that they will be standardized so that the variables will have a variance of 1. So then all the parameters here have a meaningful interpretation. Now let me explain also one subtle difference here that is important between the star command or the star keyword or symbol and the @ symbol. So the star symbol assigns a population value, but it leaves the parameter free in the model to be estimated. So this means this is not fixed in the model that we estimate later on, whereas an @ symbol fixes a parameter. So this means, for example, the factor variance here is fixed, and it will be fixed also when we estimate the model for identification. So that plays a role when we go down to our model statement, where in the model statement you can see we have also the star and the @ symbol, and this is actually a perfect copy of the model population commands up here. So this is the exact same thing, which means we're estimating exactly the population model. We're estimating a correctly specified model with those restrictions and or with the other parameters set as starting values. So now the star command means this is a free parameter, however there's a starting value. And so the starting value from the population model is used so that convergence will be fast when we run our 1000 replications. And that can make a difference when you have a complicated model and when you have starting values that are close to the true population values. It's much easier for the program to find convergence quickly, potentially. So this is why we do it in this way. So we leave the parameters here free, except for the factor variance and the factor residual variance, which are fixed for identification, but we assign the population values as starting values so that Mplus will quickly converge across our 1000 times that it has to fit this model to those replications. Okay, and then also we ask for Tech9 output, which gives us potential error messages for each replication if there's a problem, so such as, for example, a Haywood case or improper solution in a replication. It will tell us this in the Tech9 output. Next, we're going to check how many replications are actually completed by Mplus, because there could also be convergence problems. So if the sample size, for example, is too small for this model, some of the replications may not converge. And so this is what we would see here under number of replications completed, where you can see in this case all 1000 requested replications were also completed by Mplus, so there were no convergence problems. So this means, okay, this model in terms of convergence seems to be fine for a sample size of 50. However, this does not mean that everything else is fine as well. So we need to check on other things as well. So let's scroll down, and then you can see that we have sample statistics for the first replication given here, meaning means, covariances, and correlations. This allows us to check a little bit whether something looks completely crazy, meaning whether we maybe set up our population model incorrectly. In this case, there's no problem. It looks reasonable. And so we're going to scroll down further. And then what we can check first is an important aspect of fitting in SEM is model fit assessment. And so the chi-square test of model fit is often used to assess the exact fit of a model. And so one thing that we should check is whether the chi-square distribution would be adequately approximated with a sample size of 50, since the chi-square statistic is a large sample statistic, or the test is a large sample test that relies on asymptotic conditions, meaning on large samples. And so therefore it could be that a sample size of 50 is not sufficient. So how do we check that? We check that by looking at whether the expected or theoretical proportions of the chi-square distributions line up with the observed proportions that were computed based on the simulation and our 1000 replications. And so here we can see that actually the approximation of the chi-square distribution is relatively reasonable, even with a sample size of 50 for this model. Now, this would be different for a larger model for sure, but for this relatively small model, we can see that there's relatively good agreement here between the corresponding rows of this of these proportions. So you can see, for example, the 0.05 level where we would start to reject a model if the p-value were smaller than or equal to 0.05. You can see the observed proportion for that is 0.067, which is relatively close to 0.05. So we would still, we could rely on the chi-square distribution relatively reasonably because there's not a huge discrepancy here. Now, it's not super amazing, but it's also not terrible. So this seems to work also for this model for a sample size of 50. Next, we can check the parameter estimates and make sure there's no substantial bias in the parameter estimates. And we can check that for all parameters of the model, meaning the factor loadings, the structural regression coefficient, the error variances, and potentially other parameters that may be part of the model. Here we can see, for example, when we look at the structural coefficient, the regression coefficient for F2 on F1, that the population value was 0.3, so that's the value that we set in our population model, and the average estimate across the 1000 replications was 0.3167, which is pretty close. So there was very little bias in the estimation of that regression coefficient, even with this small sample of 50 cases. So that's nice, that's good. The loadings also seem fine for the most part. There's not a huge discrepancy between the population values and the estimated loadings. For the residual variances, when we look at those, we can see there's maybe a little bit more bias here on average, but it's also not terrible for the observed variables, so no substantial parameter bias, which is good. Next, we should check on standard error bias. So are the standard errors appropriately estimated? And this is checked by looking at the standard deviation of the parameter across the 1000 replications, which gives us an empirical standard error. So that would be a Monte Carlo or empirical standard error, kind of like a bootstrap standard error that we obtain from the simulation, and we compare that to the standard error average. So that would be the average standard error across the 1000 replications, because in each replication we can compute the theoretical standard error for a given parameter, and then we can compare that to the standard deviation. And here you can see that there's not much discrepancy between the standard deviation column for a given parameter and the standard error average column for the same parameter. So those are all close. For example, here for our structural regression coefficient, it's 1.1875 versus 0.1754, so not a big problem. So this means there's no standard error bias of any substantial magnitude here, which is also good because it means our tests of significance would be reliable. And then what you really wanted to know about is power, right? So power can be found also in this output, and that's the last column here. Percent significant coefficient. So this means what was the percentage or proportion of coefficients or percentage of times across the 1000 replications that a given parameter was found to be significant at the 0.05 level. You can see for the loadings on the first factor F1, 100%. So this means every single replication yielded a p-value for those three loadings that was smaller than 0.05, which makes sense because these loadings are very substantial, 0.8, 0.9, 0.85, so they were found to be significant in every single replication. No surprise here, and it's maybe not that interesting. But what is interesting is for the structural coefficient. So that's what you would care about, is do I have enough power to find that this coefficient of 0.3 is significant in a sample of size 50. And here you can see the power value for this is not great. So it's 0.438, which means that only in 43.8% of replications, or 438 replications, was the parameter found to be significant at the 0.05 level. So less than half the time, in less than half the replications, And this means the power value was low. We had low power of 0.438 because we know this parameter is different from 0 in the population, so it should be found to be significant, and yet we did not have significant power in more than half of the replication. So this is the empirical power value that you would care about, and then potentially for other structural coefficients as well. Now, there's one more thing that you would also look at in this output, and that is Tech 9. So at the very bottom, we find the Tech 9 output, and that is error messages for each replication, if any. And so here we can see that there were quite a few replications that showed error messages, and it's always the same message here. The residual covariance matrix theta is not positive definite. This could indicate a negative variance or residual variance estimate for an observed variable or other things. So this typically indicates a Haywood case such that there's a negative error variance estimate for an observed variable. And that occurred quite a few times here, which may be a reason alone to reject that sample size of 50, even if you were satisfied with the power value, which here we would not be satisfied, but if you were satisfied, you would still probably not choose that sample size simply because of all those error messages that indicate that you would end up with a high likelihood of an improper solution. So conclusion here would be sample size of 50 is not adequate, even though chi-square is pretty good, the chi-square distribution approximation is pretty good, parameter bias is not present, standard error bias is not present. However, power is too low and we get a lot of error messages about improper solutions, so not something that we would choose. So then how would you proceed in that case? In that case, you would go back and you would rerun the simulation with a larger sample size. For example, 100. And I've done that already to show you. So I have done the simulation with the same model now for a sample size of 100. So twice the sample size. And then you would look at these things again to see, is my power better? Do I get fewer error messages? So let's take a look at that. Obviously, the chi-square distribution can only get better, that approximation, and you can see that it is better. So here you can see those are even closer, those values here. And then also parameter bias and standard error bias would only get better with a larger sample, so you don't have to worry about that very much. But let's take a look at power. So here's again the power value, the empirical Monte Carlo power estimate for our structural coefficient of 0.3 between the two factors. And you can see now power is 0.713. So now in 71.3% of cases would you find this parameter to be significant in your sample. So that's a pretty decent power value, maybe still not enough. Typically we shoot for power of 0.8 or higher. So if you wanted more, you would have to go higher with your sample size, higher than 100. And then the second thing that we want to check also is, are there fewer or no error messages anymore with a sample size of 100? So let's go look at that, and we can see 1, 2, 3, 4, 5. There's still quite a few, not nearly as many, but we still have 5 or 6 of those. So there's still 5 or 6 out of 1,000 replications that showed a Haywood case. So question is, do you want to deal with that or not? If you feel like, nah, I would rather be certain that there aren't any Haywood cases, then you might have to increase your sample further. And so I did that again. And so when you take a look at 150, then the power is much improved. So let's take a look at power first. You can see then with a sample size of 150, the power value then is 0.878, which is satisfactory. And in terms of the error messages for Haywood cases, there would be only 1. So 1 out of 1,000, that's a pretty good quota. So you would be pretty safe, I think, with a sample size of 150 in this example. I hope you found this video useful to learn about power analysis in SEM. You can of course apply that to other models as well, to more complex models, and can simulate them as well in this way. Please consider subscribing to this channel. Don't forget to check out the description for additional resources, including workshops that I offer through QuantFish, and I'll see you next time.